Hi, welcome to this particular module. In the last module what we have seen how to fabricate a flexible force sensor, right, using a PDMS and P.PSS as a strain gauge material. So, strain gauge P.PSS we are using. P.PSS is a conducting polymer and it has a very high gauge factor compared to a metal. So, how to pattern P.PSS we have seen, then how to create gold contacts for the strain gauge that we have seen, and then how to create a bump and attach a bump, and finally realize the sensor by peeling off the PDMS from the substrate, and the substrate was silicon, right. Once you have this sensor ready, then you have to attach this sensor on 5 sides of a bead, and that bead we have connected to the catheter. Now, how to calibrate it, how to get the values that when you are applying a force, right, how the sensor performs, what is the output of the sensor, right. So, for that we will see the some of the experiments today. So, if you see the screen, what you see is there is a micro manipulator. This we will actually see when we will have a tour to the fab lab, and that will be part of this particular course, where you will be shown micro manipulator, its performance, its operation in the laboratory. And it is extremely important tool, because we have to indent the tissue, or we have to indent the force sensor to get to evaluate its performance, right. It is used in many applications. We will talk about it when we will go to the fab lab. It is a class 10,000 non-conventional clean room for characterizing the sensors that we fabricate in a actual conventional clean room environment. So, we have a series of lectures for you guys to see how to work in a class 10,000 clean room, what kind of precautions you should take, what kind of equipment are generally there in the clean room, what is biosafety hood, what is a peristaltic pump, how the manipulator can be operated, how the impedance analyzer can be operated, right. How is the oven operated, how you can form the PDMS from the silicon mold. So, this everything will be covered as a part of this course, and we will show it to you in reality how it looks like, right. So, it is very important to connect your theory to the experiment part, so that you can correlate what we are learning here and how the system looks like, right. So, since all the things that I have talked, we will be talking in our course, whether it is micro manipulator, or it is your impedance analyzer, or it is your peristaltic pump, or it is your incubator, or it is a biosafety hood, because everything we will be using, right. So, we will see when the time comes. Right now, if you see, we have a commercial force sensor connected to the micro manipulator, and then with that commercial force sensor we are moving the micro manipulator down like this, and we have this flexible force sensor. So, when we apply a force here, right, the sensor would change its output, right, sensor would change its resistance, because it is a strain gauge. So, we have developed an electronic module, so that the value of the strain gauge can be converted into voltage, and that is why wherever you see the plot that we have, the plot that you can see here is compression force versus sensor output voltage, right. So, you can see here the compressive force and versus the sensor output voltage. Here you can also see that we have used the we have fitted the curve, and the R square value is close to 0.9872. That means the sensor output is linear, right, it is a linear result. Same way we have used when it is Fx, that is the x direction, when we are forcing in a y direction. So, you can see here x, y and z, right. So, x direction when we force apply force, when we apply in y direction, and we apply in the z direction. For all these three forces, we have corresponding results from the output of the sensor. So, you can see sensor output voltage for your Fy, right, and again you can see R square value 0.9984 for your Fz, right. Again you have compression force versus your voltage. Compression force is given in newtons. So, that is one thing. Now, calculated contact force versus sensor output voltage. So, now if I keep on applying force, what is the on how the sensor output would change. So, you can see here from 0 to about 4, close to 4 or close to 3 grams, the sensor will not is not able to it is almost like point from 0 to 4 or 0 to 3, the sensor is not so sensitive, right. About 3 and above, the sensor will start showing the change in output voltage. You can see here 0.2 volt from 0 to 4 is almost like minimum, right. So, and we do not worry, we do not have to worry about this particular force. In fact, until this force we do not have to worry, because the optimum force is 40 grams, right. Optimum force is 40 gram during surgery. So, what we see is until 5 grams of force we have about 0.4 and it is not really linear, but you consider from 5 grams and above it is linear, right. So, as you increase the force, the sensor output voltages, and there is a linear relationship between the force and the sensor output above 5 grams, right, or 5 grams and onwards. So, that is one thing that we can see here. Second thing is calculated contact force versus measured contact force. So, if we already know how much force we are applying, because we have a commercial force sensor here, right. So, we know what is the calculated contact force, and correspondingly what we are measuring. So, for 10 gram, is it matching? You have to see like this, close to 10 gram, right, 20 grams somewhere here, right, 20 grams is there is, you can see here, right, and 30 grams like this. So, calculated force versus measured force, you can again see a quite linear relationship with R square value of 0.9981, right. So, this is we can see that it works very well. Another thing that you can see here, we have used a force sensor MDB 2.5, which is a transducer technique from United States, and there is a metal stick, and this is a gelatin box, right. This is a gelatin metal box. So, we are pressing this force sensor against gelatin and getting the results. Same thing what we have done, we have connected the catheter, and we are forcing the catheter against the gelatin and we are collecting the results, right. So, we are comparing our results with the commercially available force sensor, right, and when we apply different forces, let us say 5 gram force, right, we start applying 5 gram force and then we stop at certain point, it will come back to its original stage, but there is a for 5 grams the output voltage is different, for 40 grams is different, for 60 grams is different. You can clearly see that the sensor can be used from 5 grams to 60 grams, and it shows on off time. It can show on off time, and it is when you apply a force 60 gram, it becomes saturate, it is not continuously increasing. Then it is very difficult to get the understand the performance of the sensor. So, here what we can see is the sensor can be utilized to understand its performance by calibrating it with respect to the commercially available force sensor. Now, this is another thing that we have measured, and that is what I told you is, in reality the catheter would be inserted in the body and there is a flow of blood, right. So, the data that we obtain from the flow of blood should be neglected, and the data that we get only from the sensor, only when the sensor is touching the tissue should be taken into account. So, for that what we have done is, we have sensor 1 here, sensor 2 here, there are 2 sensors here, and then there is a water, this is a x direction and then there is a z direction, you can see here, right. So, what we have done, we have moved the sensor in x direction and z direction. So, we have dipped the sensor in this direction and we saw what are the results. So, if you see this sensor, there are two sensors attached, right. One sensor is in this particular it is at the bottom of the catheter or bottom of the bed, and second sensor is on the side of the catheter bed. So, if you see for sensor 1 and sensor 2 we have different results. However, just looking at the results, what we see is FZ1 and FY2. So, FZ1 is your FZ1 is this one and FY2 is your this one, right, because for this one is Z, but for this one it will be Y, right. This is a normal force to this strain gauge, it is a y directional force or a shear force to this particular sensor, right. What I mean is, you apply a force like this, it is a normal force, but if a force is coming in this direction, it is kind of shear force, right. So, we are measuring the normal and shear forces or force in different direction to be precise. So, Fz and Fy2 we have the results, right. We can clearly see that when there is a Fz force, this sensor will be more sensitive compared to this sensor. Same way Fz2, that is the when we apply the force in this direction, which will be directly pressuring the sensor here, right, it is way higher compared to Fx1, which is the force in this particular direction. Thus, what we are just measuring is what kind of data we can obtain when the sensor is moved inside the water, and what will be the flow when we actually put the sensor in the heart. We have to study that. We have to also change the design of this sensor, like I said, right. So, the idea of this particular module to show it to you was that we can design a flexible force sensor, we can obtain the data using flexible force sensor, but we have to optimize our design, we have to improve our design to actually use it in the surgery, right. But these are the preliminary results that we have obtained, and from this we get a confidence that using the strain gauge and P dot PSS material as a strain gauge, we can measure different forces, right. So, this is all about the using the 3D MEMS based force sensor for catheter contact force sensing. So, what we have learned in these 3 modules is that you can design a flexible force sensor or any other sensor using microengineering. Second is what is atrial fibrillation. Third is what is a tool to cure atrial fibrillation. Fourth is how the surgery is performed. What is electrical mapping, and then how the another catheter is inserted when you are performing ablation. Fifth is when you want to fabricate a flexible force sensor or any sensor, you have to calibrate it, and then you have to see its performance by considering all the possible scenarios that you will be that you have to take into consideration when you are comparing the actual catheter when it is placed or it is used inside the body, right. So, this is about the catheter contact force sensing for atrial fibrillation. Now, the topic is smart catheters. So, how you can make it smarter? How you can make it smarter? You can we already talked about making it smarter by using electrical mapping, because there is a catheter which is lying inside that tomb. When tomb opens, the catheter will come out, it will do electrical mapping, it can go in, tomb closes, it can be used for ablation. So, doing multiple things is smarter catheter. Force sensing ability will be a smarter catheter. Another ability would be tactile sensing. When a surgeon is operating this catheter, can a surgeon feel the force, right. So, that is a feeling of that force will be the tactile sensing. If you have tactile sensing on the force on the contact along with contact force sensing, then this catheter operation would be easier most probably, and of course, the catheter is smarter because it can not only show you the force that you are applying, but also you can feel that force, right. So, how can you now develop a tactile sensor? I leave it on you. Now, you know how to perform a microfabrication, how to use photolithography, and try a few ideas. again in all these things that we have discussed, if you are stuck somewhere, if you have questions, if you have queries, you should, and I insist you to ask us using the forum, right. Your queries would be answered to the best of our abilities, and feel free to learn more, right. Feel free to learn more, get a novel ideas and try to implement those ideas, at least in terms of designing the process flow for fabricating a particular sensor, right. So, having said that, we will be looking at other applications related to clinical research or clinical relevance of our MEMS space sensors or microfabrication. Till then, you just go through this particular module and previous 2 modules to understand the complete concept. I will see you in the next class. Take care.